let's take a look at series circuits, the characteristics. First, there's something that's really simple and easy to calculate. If you have a circuit in series, that just means one component after another. So let me draw a picture. First of all, if we go back to our analogy of the hose or the pump and the tank of water, remember the charge was like the actual water. The pressure was the voltage, and like the flow of the water, that was the current. And then like resistance would be something in the way, like a rock or something. So if we have a series circuit, there's only one path for current to flow. So the current everywhere, the current that's flowing through this is going to be the same amount of current flowing through this, flowing through that, flowing through that. There's only one way for the current to go, so the current is just constant everywhere on this circuit. So the current flowing through every component is equal. And then there's a rule for resistance. Each one of these resistors, whatever they are, the total resistance of the entire circuit, the way you calculate it for series, is just by adding up all the circuit, or adding up all the resistances of each individual component. So to calculate the total resistance, which is denoted by R sub T, Rotten Tomatoes, you just add up the individual resistances of each component. So you're just adding them together. The last thing is when you're calculating the voltage, it's the same way. For series circuits, then you just add up all the individual voltages, and that will give you the total voltage. So there you go. That's to calculate the total voltage. For circuits that are in parallel, it's a little bit different. They have different rules. Alright, so we have this. For the series circuit shown, find the total resistance, find the current through each component, and find the voltage across each component. This should be pretty easy because we have those rules. What are those rules? Well, first let's find the total resistance. What is the resistance? What did we say? To calculate total resistance, use this. So you just add up all the resistances. Well, we need to know that, and I didn't write it down. This is part of the problem. Okay, there we go. So the total resistance is just the resistance added from each component. So I would say RT, rotentemeters. RT is just going to be R1 plus R2 plus R3. So that's 220 ohms plus 470 ohms. Make sure you're putting in your units while in your calculations. And then 1,200 ohms. Okay, that's pretty good. What is that? That's 1,890 ohms. So that's pretty cool. There, done. Bam. Check. So that's the total resistance of the entire circuit. So we have that. Okay, very good. Find the current through each component. That one's also really easy because here, this is a series circuit. So the current flowing through every component is equal. There's only one way for current to flow. So IT is just the same all the way around. Okay. Wait a minute. How do we get that though? How do we have that current? We have to use Ohm's law, right? We have. Let me draw that. Ohm's law says that these three things are related, and these are going to be totals. Maybe you should write T. These are all totals. Okay then. The voltage, the total voltage. What's the total voltage? It's just the voltage of all the voltage drops added together. That's what it says there, up there. But we're given the total voltage. Look at that. Look at that. Oh, it's very good. Very good. So we have the total voltage. I'm going to put a little check mark there. Sweet. The total current we don't have, but we just got the total resistance. So I think I'm going to solve for IT. by doing by going so the total current, that's going to be equal to the total voltage, which is 12 volts, divided by the total resistance, which is 1,890 ohms. So then we get the volts is 12 volts. How do I know it's 12 volts? Because it tells me. And then divided by 1,890 ohms, and that becomes amps. So we get 0.006349206 amps. That's an amp. There we go. No period. Why did I do that? Okay, yeah, cool. That's very, very small. Later on we'll use like milliamps or kiloamps or whatever. So that's nice. That's pretty nice. What about the current between each component? Because that's what it wanted, right? Well, the current through each component, it's the same. The current flowing through every component is equal. So IT also equals IR1, IR2, IR3. Right? All of these currents are going to be the same because it's a series circuit. So there we have it. Now I'm going to check that off. And then voltage across each component. Well, how do we get voltage? Well, let's see. Oh, it's just all those added together. For this, we can use Ohm's law once again, except for instead of VT and IT and RT, we'll just be doing Ohm's law with each resistor. So let me draw this little circle again, and we're going to be doing it 3 times. It looks like because we have 3 resistors. So circle. Let's say the voltage drop across resistor 1. That's going to be equal to the current through resistor 1. And or equals time. The voltage drop is going to be the current times the resistance. All of that for the single resistor. So I'll just what are we solving for? I forgot. Voltage, right? So that just means V1 equals I1 times R1. And I1, well, we already know I1 is that many amps, right? We know that. Okay? And so I'll put that in. And then the resistance is, oh, that's given, right? The resistance is 220 ohms for R1. So V1 will be, well, I guess I have to write it. So we have that, and it's the voltage 1.3968. I'm going to leave it there. And volts, right? So that's V1. And it's asking for voltage across each component. So the voltage drop on the first I guess, resistor, yeah, is 1.3968. So that's pretty cool. And you do the rest in the same way. If you want to pause it and then figure out the rest, that would be good. And then unpause it, and I'll just show all of the answers for that. So pause it. Try it on your own. And so there we go. There's the answers for that one. Voltage drop across the second resistor is 2.9841 volts, and the voltage drop across the third resistor is 7. Oh, admin to D. You get scared? Little bit. That was okay. Yeah, 7.619 amps. No, not amps. This should be volts. What is this? What is this? Okay, so what does this mean? Well, look at this. It's a voltage drop. What was voltage in the analogy? Voltage was the pressure, right? I think so. The pressure. Okay. Right? Wasn't it pressure? I think it was pressure. But look at it this way. We have a really high resistance for that third resistor. So the voltage drop, the pressure drop over the third resistor is really high. Okay, that's cool. And then the pressure drop for number 2 is the second highest because it's the second highest resistance, and then the voltage drop for the first resistor is the least because it has the smallest resistance. Okay, that's a 10-minute video. Sorry for that, but you know what? We'll be done. We'll get to parallel circuits later. There you go.